remind ourselves of the floating point formats, the sort of three of them that we can do. And there are more than these, but we'll just kind of concentrate our attention on these because these three, just for sake of sanity. We can do 16-bit, 32-bit, or 64-bit floats, and the allocation of the bits. Everybody gets one signed bit. That makes sense. The number is either negative or it isn't. But then how many bits we allocate for the exponent and for the mantissa are those things. And then the bias is that. And the formula, by the way, for the bias is bias equals 2 to the number of bits minus 1 minus 1. Okay, so for example, for the 16-bit float, the bias was 15, and so that would be 2 to the 5 minus 1 minus 1 is 2 to the 4th minus 1 is 16 minus 1 is 15. And it works for the other ones too. So this is sort of the general formula for how you get the bias with sort of most of the, quote, standard schemes. There are some kind of weird specialized ones that are used in like, so there's some 16-bit schemes that are used in like machine learning applications. And then I actually, when I was reading about this, there are a couple of kind of, I was a little surprised, frankly, weird 24-bit schemes that are used, like, for example, I think Pixar has a special format that they use in like their rendering for the movies and stuff. That's a little different. I was a little surprised, 24-bit is, I suspect what they were doing is that 16 bits not good enough, but 32 bits is overkill. And so they were trying to find the happy medium in between where 24 bits is a smaller bit amount, and so maybe they could accelerate things a little bit versus 32-bit. And if you're rendering an entire movie, well, that maybe is an important kind of thing. So anyway, but that's the formula, at least for the IEEE ones, compliant ones. Okay, so what I wanted to do next is do some arithmetic with it. So we've encoded and therefore decoded floating point values, right? If we've got a number, we can go through the arithmetic to figure out, okay, how do we represent this thing? And so for sake of demonstration here, let me just pick kind of two numbers seemingly at random. Any suggestions on numbers? Well, what was one of the numbers we worked with last time? I think we did 10.5. Yeah, okay, so let's do 10.5, and let me just, let me copy, um, this. Okay, so this was 10.5, and let me get rid of the orange lines. Okay, and then fix it so it was a 0, and then 0, and then we had a 0 and a 0. I think that's it. Yeah, okay. Okay, so this was 10.5 as a float 16. All right, so somebody give me another number. 42. Okay, 42. I'm just using the float toy to speed this up here. Is this. Okay, so the number here is not particularly important. I just want an example, okay? And if we were to add these two numbers together, then obviously we should expect the answer to be 52.5, right? And now, what can happen when you add two floating point numbers, particularly if there are lots of ones to the far end of the mantissa, is that you might actually lose precision in your answer. We won't have that problem here, partly because we've got all those extra zeros at the back, and because the two numbers are pretty easy to begin with, right? But if I were doing like, pi to as many digits as possible, and say e to as many digits as possible, I might be off slightly in that last one or two decimal places, just from rounding error, essentially. Okay, won't happen here. So let me write 10.5 in the following way. It's one point mantissa, and I'm going to suppress all the extra zeros just for cleanliness. Okay, times 2 to the, well, what's the exponent's value here? So what does this look like as an unsigned integer? In 5 bits? 16, okay? But it only counts as a 1. Why? Because of the bias, okay? So the encoded value is 15 bigger than the actual value. That, and why that's a good thing will be clear in a moment. Then on the subject, what's the exponent here? Looks like 20, but it counts as 5. Okay, so 10.5 is this. Okay, hold on. I think I've made an arithmetic mistake here. No, I'm looking at 10.5. All right, let me just double check that I didn't make a mistake last time, because that doesn't look correct for 10.5. Um, oh, that's why. I miscopied. There was another one there. Okay, in the exponent. Okay, so let's fix that. Okay, so it should have been a 1 here. Yeah? Okay, which makes the exponent look like what? 18. And so it counts as 3. Okay, there we go. Um, oh, okay. Well, those are unsigned integers, right? So I've got the 1s, 2s, 4s, 8s, 16s places, right? And then I just add it up. Um, yeah, and the exponents, you always treat them as unsigned integers, not signed integers. The bias is y. So even though they're like, we can have negative exponents, we never store them as signed integers. We store them as unsigned. And that may seem silly, like, why do that? But because of what we're going to do in like 3 minutes, it makes sense. Okay. Okay. So this is what it, oops, not erase it. That is 10.5, right? And if I move the decimal point, or the radix, excuse me, 3 positions to the right, I get 1010.1, which is 10.5, right? So it's all good, right? Yes? All right, if I do the same thing with 42, then it's 1 point, what was it? Interestingly enough, its mantissa is the same. Huh? Oh, it's, yeah, let me double check it. Sorry. Okay, what was the number 42? Oops. No, it's 0101. Yeah. Yeah, it does. I think I just was, yeah. Okay, I'm double checking it here, so it's good. All right, so by coincidence, the mantisses are the same. Okay, just, yeah. Those are the numbers you picked, so whatever. Um, okay, so I want to add these two numbers together. Yes? And we, of course, know what the answer is supposed to be mathematically, but that's sort of cheating in some sense. Yeah? Okay, so how can I add these two numbers algebraically? Sort of what's the problem here? Hmm? They have different exponents, okay? And if they had the same exponent, then I could factor the exponent term out and just add the what was left and then have the exponent. Okay, but they don't. They have different exponents. Okay, and so what I want to do is, well, first off, looking at the two exponents, even just in binary, is it obvious which one of the two is bigger? Okay, this is why we store them as unsigned integers, because it makes the determination of which exponent is larger almost instantaneous. Okay, so the second number has the larger exponent. Okay, so now let's think about it this way. The answer we know is supposed to be 52.5, right? Okay, so let's suppose that, and this is maybe a bad example, but let's suppose that I'm only going to let you write down two digits for your answer, exactly two digits. Okay, would you rather write down 52 and lose the 0.5, or would you rather write down 2.5 and lose the 5 that's representing 50? Clearly, you would rather write down 52, right? Because you are, yes, you're still off, but you're off by a smaller amount, okay? So what that means is if you're going to lose precision, you'd rather lose precision in the lower significant bits, which is to say the things further to the right, okay? And if there's going to be a loss of precision, it's going to come from changing one of the two numbers to have the exponent to match the other one. So what I will do is I will take the smaller number, okay, the one that has the smaller exponent, and I'm going to deliberately denormalize it by futzing with its exponent, okay? And now in this particular example, we won't lose any precision, everything will be fine, but we could theoretically because of what I'm about to do. Okay, so can I rewrite the first number as 0.010101 times 2 to the fifth? Yes? Okay, so all I did was I shifted the mantissa and the one that was in front of it, okay, two positions to the right, and then correspondingly upped the exponent by 2. Okay, so you guys agree that that number is the same mathematically, but it looks different. Okay, by making them have the same exponent, that means that I can do the following. I can say, all right, I'll do 0.101, or sorry, 0.010101 plus 1.0101 whole thing times 2 to the fifth, right? If both terms have a 2 to the fifth, can I factor that out? Yeah. And so now I can, at least for the moment, ignore the exponent business and concentrate only on the mantissas. We? Okay. So now I've got some arithmetic to do. So 1.0101, and I'm going to write 2 zeros there just for cleanliness. 010101 plus. Okay? So that's what I need to compute next. Okay, so what's the sum here? Well, I get a 1 there and a 0 there, no big deal. I get a 0 here and a carry, a 1. A 0 here and a carry and a 1. The radix and a 1. Okay? And this whole thing is still times 2 to the 5th. Okay, so there's my answer. Okay, so my answer is, the number is 0 for the sign bit. What's my exponent? 5, which what do I encode that as? 20, which would be a 16, no 8s, a 4, no 2s, and no 1s. And then what's my mantissa? 101001. And let's see, that's 6. I need 6. I need 4 more zeros to get it up to 16-bit. Okay, so there's my answer. And let's double check with the float toy that that's in fact correct. Just to make sure that I'm not being a moron this morning. Okay, so what did we get? So 1 0. Yep. So it worked. Okay. So in this particular case, we didn't lose any precision. And what would have happened if we had lost precision? It would have been when we shifted this number here. Let's say that there were lots more 1s over to the right. Well, some of them, when I shift too far, I still only have 10 bits for my mantissa. Well, let's say that I've got all 1s and I start shifting things to the right. What's going to happen with the 1s at that far right end? They're going to fall off the apple cart. Okay. And therefore I'll lose precision. Didn't happen here, but it could. Okay. Does that kind of make sense? All right. So the procedure for addition, right, is you have to get, the first step is to make sure that the exponents match. Once they match, you can then do it and kind of go from there. So the real steps for addition are, let's put it this way, denormalize number with smaller exponent, add, and sometimes you have to renormalize the answer, and that'll happen if there's a lot more carries than what happened in this example, but you could have to do that. Okay, so that's essentially the steps for it. Okay, and let's say that you wanted to do, well, subtraction. Well, you subtract instead of add, but you still have to denormalize. Okay. All right, so that was, we just did it in 16-bit for sake of cleanliness of writing. I think the exercises I gave you have you do it in 32-bit, but it's basically the same thing. Okay, what's different about 32-bit versus 16-bit? What 3 things are different? The bias and how many exponent and mantissa bits there are. That's the only difference. Okay, Gucci? Okay, so wonderful. Any questions about that? Yes, sir. Oh, that code? Uh, oh, yes. Those are the different standards for this. And these for floating point. Because it's a standard, right, you can find all of the standards everywhere online, right? Wikipedia's article on IEEE is pretty good. Um, and what's nice too is that they have some other examples of encodings besides the ones that I did, right? I tried to deliberately pick numbers that weren't the same as theirs. The book also, or books also have some examples. But yeah, the 16, 32-bit, 64-bit, there's oodles of examples out there. Okay. Um, and so now you guys should have every tool you need to do the second paper assignment, which was the basically to do, well, what was the first paper assignment? To do a bunch of integer stuff by hand. Well, the second one is to do a bunch of floating point stuff by hand. Okay. With that, obviously, don't be a moron. Double check that your answers are correct with Float Toy. Right. It's a perfectly good tool. So, okay, good. All right, let's do some coding. So let me return to, for sake of fun and exciting demonstration, this really, really interesting piece of code. Okay. Now, we're looking at basically 20-ish year, 20, 30-year-old code. Okay. So there's a few things that we have to do to to when you're reading old code, which is, what is a long? A long int. What's a long int to us? Huh? Well, yes. Okay. A long int, if we're writing code, means a 64-bit integer. A long int back then meant a 32-bit. Okay. And the reason is that no desktop processors had 64-bit capability. They were all still 32-bit. Okay. Um, and so an int back then meant a 16-bit thing, and a long int meant 32 bits. Now, what does an int mean for us? A 32-bit and a long int is 64-bit. Okay, so that's the sort of only thing that we have to remember. And then this um, float still does mean 32-bit though. Okay, and right. Okay. So what I want to do is kind of show you how to translate this algorithm into assembly. Okay. And um, so let's go to here and let's do, oops, that's not what I meant to do. I want a new file, and let's make this text file. Let's save it, and we'll call this carmack.asm. Okay, and switch to ARM 16, 64. Okay. Okay, so the usual stuff we need there. Okay, so we got our usual things. All right, so I'm going to make a number here, or a string, and let me say my string, or let me just call it string 1, is well, let me say number. We can't use a colon. So number equals, and then I'll do percent F. Okay, so I'm going to say this. I'm going to print three numbers: an input number, the first step of an estimation, and then the second step of an estimation. Okay? Seem all right? Okay, so the other thing I want to do is actually I'm going to split the window. I'm going to make a new C file here for reasons that'll become, okay, and let me actually take John Carmack's C code and just copy that, and I'm going to put it here, and then I'm going to get rid of the terminal for right this instant, okay? And the reason I want to have, and let me also get rid of the Explorer just so we can see things a little bit better. And then let me see if I can shrink a little bit of this. Okay. So I need to have a long number I, okay, meaning just an int, okay? I also need to have two floating point numbers and this constant 1.5, okay? So I'm going to, in my data section, 3/2 is going to be a word, and then I'm going to cheat real quick and compute what 1.5 is. As 3FC. Okay, so that's 1.5. 0.5 is okay. And the reason I'm going to use that is because in my code here, there's a point where I multiply by 0.5, and I also, there's a point where I multiply or do something with the number 1.5. So I'm just going to go ahead and predefine those as something in memory so that I've got them ready to go when I need them. Okay, is that all right? Yeah? Okay, so I've got those two numbers, and I also need a number to work with here. Now, the point of this program or this little snippet is to compute 1 divided by the square root of a number. Okay, so what would be a good number to demonstrate this with? Let me use 2 as our number. Okay, the reason being, what's 1 divided by the square root of 2? Do you guys happen to remember? You ought to, because that's the sine of 45 degrees, which is 0.707 blah, blah, blah. Okay, so I'm just going to pick that number, 2, because it's something that I know the square root of it exactly, okay, and, or not exactly, but essentially exactly, and in, it just so happens to be that when you encode it. Okay, good? All right, so got to have some sort of number to work with. Okay, so step 1 is I need to, my number here is this number, okay? And I've got these numbers basically just sort of predefined. Okay, so fine, but I need to do this. X2 is going to be a number times 0.5, okay? So, oops, let me go in and define, let me define var I to be, and let me just initialize it to 0. Let me do var x2, initialize it to 0, and I'm going to define var y there. Okay, so all that means is I've defined, basically, I've allocated memory for the number I, the number x2, and the number y, and I've got those other constants. So I've just allocated some memory to store these things. Okay, is that fine? And initialize them to 0 because, of course, their value is going to change as the program goes on. Okay, is that okay? All right, so line 7, x2 is number times 0.5. All right, what's my number? I'm calling it my num. And you know what? Actually, just for cleanliness, let's just call it number. And that way it matches the C. Is that okay? Yeah? Okay. So x2 equals number times 0.5. What do I need to do to compute that? Well, first thing, I need the number and 0.5 to both be in registers. So how do I get the number into a register? I need to load x0 with its address, and then I need to load, you fell for the trap. I want to do something with x0 with the brackets. That is correct. But what needs to go in front of that? Where do I want to put the number? Patrick was suggesting x1. Why is that incorrect? What kind of numbers are we working with here, gentlemen? Floating point numbers. And where do floating point numbers go? The floating point registers, which are S and D. Okay, now in this case, what do I want? S or D? Yeah, forget which one's which. Well, what does S stand for? S clearly stands for socks, which is a description of y'all's memory. Super awesome. No, it does not stand for that either. Single, as in single precision, right? What kind of floating point numbers are we working with here? Single precision, because they're 32-bit. Okay, so I need to load that not into an X register, but into a S register. And is that valid for me to load it into S0? Is S0 have anything to do with X0? No, they are physically completely separate objects. Okay? All right, so that loaded in the number. What else do I need to load in? The number 0 or 0.5f is, what did I call that? 1/2. Okay, and so I'll also load that in. Well, I can't actually do this and just reuse it. Okay, so that loads in the two numbers, and what do I want to compute? What's the first line here of the code? Yeah, to multiply them. So I need to multiply, and it's fmul here because it's a floating point. So let me put the answer in S2, and I'm multiplying S0 and S1. Okay, so S2 now has 0.5 times the given number. Okay, now in our case, because the given number was 2, then x2 would be, in this case, just 1. Okay, but that's only because of the example I picked. Okay, let's store that back out to memory. Where do I want to put that answer? x2 was the variable I called it. All right, so let me load register 0 with the address of x2, or not x2, var x2, and let me store s0, s2, sorry, in the spot pointed to by x0. Okay, so now out in memory, x2 has been updated to its new value. which was the value just 1 in this case. Okay, is that okay? All right, so that was one line. All right, y equals number. Well, this won't be too hard. Let's load x0 with the address of var y. Let's where is the number? It's currently still in S0. So let me store S0 to the thing pointed to by X0, and that'll get that number there. Okay, and now comes the fun part. What on earth does that line mean? Okay, so stare at it for a moment and tell me what kind of stuff are we dealing with there? Okay, in C, if I have a variable y, which I do, right? What does ampersand y mean? It's the pointer to y, okay? So what that line means, okay, is I'm doing a type conversion. I'm going to take the floating point number y and take its bits out of memory and pretend that it's an integer. Okay, so in memory, there's 32 bits worth of stuff, right, for that number, and they're encoded in floating point. So there's some ones and some zeros, and there's 32 bits worth of them. Can I take that 32 bits and go over and shove it into an integer register? I can, right? Now, if I do so, is it still, like, am I treating it as a float anymore? No. For the moment, I'm going to pretend that that bit pattern represents an integer. This is the crazy part about this algorithm, okay, that this actually works. Okay, so here's what I'm going to do is I have the number y is I just stored something to it. So, okay, so let me load y in. Where is y in memory? There, okay. What I'm going to do, well, actually, let me do it this way. Okay, so now S0 has the number y in it as a float. Yes? Okay, so that floating point number is really just a crap load of bits, right? Can I just wholesale move all of those bits over into an integer register of 32-bit width? Sure. And here's how I'm going to do it. Okay, I'm going to use the command fmove. So I'm going to take S0, which currently has a floating point number in it, and just march all of its bits over into an integer register. Now that sounds crazy, and it kind of is, but just work with me. Because here's this crazy number, so subtract and bit shift me maybe? It was an attempt at a joke, right? We just met and this is crazy, but here's this number, so subtract and bit shift me maybe? Ah, come on. Okay. Way too early for that. Okay, so this line is basically taking a floating point number and just moving its bits into an integer register, because the next line is I'm going to manipulate it as if it's an integer. Okay? All right, now I have to have this crazy number. So let me go up and define that. And I'm going to call it magic 32 because there's a different one for if you do this in 64 bits. Okay, where did that number come from? I don't want to tell you that right now. It's magic. Okay? All right, so line 10, I need to load, well, first thing I need to do is, what does the double greater than symbols mean? Nope. In math, it means strictly greater than, or like really, really greater than. But what does it mean in C? Hmm? Nope. It's a bit shift operation. Okay. It's a caret? No. So bit shifting, right? If I have an integer, right, and it's got a bunch of ones and zeros, what happens if I shift everything one bit to the right? I get a new integer, right? But what's the relative value of the first one versus the second one? Oh, sorry, the second and the first, whichever order. Huh? Close to half, okay? And close because of what's could happen. Well, okay. Let me just there's only one edge case. All right. What is this number? 16, 420, 420 plus 2. So this is 22, right? All right. Shift everything one position to the right, and anything that goes past that line falls off the apple cart. What is this number? 11. Okay. Shift it again. What is that number? Shift it again. Shift it again. Okay. So when I do the shifting, I'm basically chopping the number in half, but there's one minor problem. I'm chopping it in half and discarding any remainder, okay, because I'm still working with integers. So if the given number that you start with is even, you get precisely half of it. If the given number you start with is odd, you get half of it, uh, yeah, -1, but you're discarding the remainder. Okay, so you're which is the -1, right? Okay, so this is integer division is accomplished by just shifting the bits one position to the right. Now, why does that make sense? Well, what happens if you take a base 10 number and you shift its digits to the right one position? You cut it down by a factor of 10, right? And remember me working at Cole's story? It's the same thing in integer land, except you might be discarding some remainder. Okay, so in integer like base 10 land, if you shift your digits, uh, you might lose a 0 through a 9. You don't know what it is. But in binary, you're either going to lose a 0 or a 1. If you lose a 0, no big deal, nothing happens. If you lose a 1, you're off by 1. Okay, or off by a remainder of 1, better put. Okay, does that make sense? Yes. Okay, so that's all that symbol means, is to shift all the bits right one position, which is kind of like dividing by 2 where you discard the remainder. Okay, so I need to do two computations on line 10. I need to shift everybody one position to the right of the number I, and I also need to subtract it from this crazy magic number. Yes? Okay, so um, the number I, um, oh, I misread, guys. I'm sorry. What do I need to load into here? Not var y, but var I, because that's what I'm shifting. Okay, hold on. I think I made a mistake here. So var y, I stored the value into. Okay, I think I've skipped a step, guys. Hold on. All right, so what did this whole chunk do? This loaded and computed num times 0.5, right? And stores it out to x2. Y is the number. Okay, so I did that. And then, oh, I see. I just forgot this. Okay, this should be var y. I just didn't finish. Let me load register x0 with the address of var I and store w0 s0, no, w0 to the thing pointed to by x0. Okay, so here, right, I did a computation to compute I. I need to store that out to memory. Okay, so this whole section computed line 9 of Carmack's code. I did the type conversion. I took the number y, I pretended it was an int, I shoved it over into the integer registers, and I'm calling that variable the variable y, or I, excuse me. Okay? Yeah? Load in the number y, shove it and pretend it's an integer, store its value to the variable I. Okay? Now what am I going to do? So where is my variable I in the registers currently? It's currently sitting in register 0, W0. Okay? I need to shift it one position to the right. Yes? Okay? So let's do that. And the command for this is logical shift right. Which register do I want to shift? W0. I'm going to put the answer in W0. And how many positions do I want to go to the right? 1. Okay, just 1. Okay. Now, I also need to have this funky number in memory or in a register. So let's load x1. I can't use x0 for this with the address of the magic 32 constant. And let's load w2 with what's pointed to by x1. Okay. And now what do I want to do? I want to subtract the shifted version, which is sitting where? W0, from this magic number. Yes? Okay, so I'm going to subtract, I want to subtract W0 from W2 and put the answer where? W1, that's fine. We'll put it there. Actually, let me put it in W3. Okay. Because I need to also do some memory stuff. Okay, so I've just, the result of this computation is now sitting in register W3. Okay, and let me go ahead and store that back out into memory. Where do I want to put that? In the variable I. Okay, so I need to load x0 with the address to put it, and then I need to store W3 in the place pointed to by x0. Okay, so this computes line 10. Okay, good. All right. So, line 11, I have this integer. I'm going to move it back to a floating point register. Okay? So let me move it back to S0. Okay? So this is the magic of this whole thing. I'm going to take a number that's a float, pretend it's an int, shift it by 1 and subtract from this magic number, and move it back over to floating point land. Okay? Sound okay? All right. Let me stop right here and let's actually just run this and make sure that things are starting to look okay. Okay, so I'm going to put a breakpoint at line 60, which means it will do everything up to line 45 and then pause. Okay, is that okay? All right, so what did I call this, Carmack? Yeah, well, I need the debugging flags. All right, what did I say it was, line 70? 60. Okay, so it's about to finish. Okay, got some gobbledygook in the registers, but what is in register S0? Hold on. Okay, I think I've messed something up because what's in register S0? 1 times 10 to the 19th, and that's not correct. Yeah, okay, so I probably messed something up here. No, it doesn't. I just messed. I've mixed up a register someplace. Um, all right, W2 is my magic number. W0 is my shifted number. Put that in W3, loaded the variable. Okay, you know what? I'm going to get rid of a lot of this load and store stuff. You know what? Let me just clean this up and start over. I've been inefficient about this. Okay, let me just do it this way. I'm going to stop worrying about loading and storing stuff. Okay, so I need the number. Well, no, I shouldn't have done that either. All right, well let's just figure out where I screwed up here. Okay, so let's just step through it. Um, okay, so I loaded in 2 as my test number, and the number 1 is in S0. Okay, so that's good. So that first chunk worked. I'm going to store that out into memory. Okay. Um, oh, hold on. I think I see the problem. No, Y is the number. Okay. So Y is my number. Good. Um, I just moved it into W0. Oh, here's where I screwed up. Yeah, my bad. Okay, let's go back to the code. Um, no, hold on. Load X0. Okay, it's right after the F move command. Oh, yeah, okay. I should have done x1 here. So let me reassemble it. Okay, so I've got 2 there. Um, that also shouldn't happen. Okay, so let's see what else I've. Huh? Did I? Okay. Oh, yep, you're right. Thank you, Patrick. Oops. There we go. Okay, perfect. So remember, what are we trying to compute here? What's the whole point of this little snippet of code? I'm trying to compute 1 divided by the square root of a number. Okay, so what's 1 divided by the square root of 2? Well, that's the same as the square root of 2 divided by 2, right? Because I can rationalize. And I picked this number because the square root of 2 over 2, right? You probably encountered a lot in trigonometry, right? It's a sine of 45 degrees. And what is that? What's the correct answer? 0.707, blah, 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 right? And so I picked that number because that's a decimal representation that, like, you ought to recognize because you took trig and it's just stuck in your memory, okay? All right, so the whole point, okay, so let me back up. Why did I not just use the FR, like the square root command here? Or rather, why did Carmack not do it back in the day? It didn't exist in a lot of hardware, okay? So not all floating point hardware back then had a floating point square root unit. Okay, if you don't have a floating point square root unit, or if you do and it's really slow, what do? You got to do something else, okay? So we saw last time with the square root estimator, right, that I had that magic trick, or not so much magic trick, which was make a guess and then pipe it through a little formula that you can iterate over and over, okay? And that formula just so happens to be an instance of what's called Newton's method. But for the moment, let's forget that, right? So let me go back to that formula from last time. It was this, right? So what if I wanted to take the square root of a number, I made a guess and then iterated, averaging it and its sort of reciprocal and doing that over and over again. And we saw that the estimates got better and better each time I did that, right? But what was the hard part, or what was required before I could use this little iterative algorithm? I had to have an estimate of the answer. Didn't have to be a great estimate, but I needed an estimate. Okay. Is it pretty easy to guess what the square root of a number is close to? Yeah, not too hard, right? You just forget the decimals and just say, okay, 10. That's between 9 and 16, and it's a lot closer to 9. So I'd expect that the answer is going to be 3 point something. So 3 is a good guess, right? That was easy, okay? But I'm not doing square roots. I'm doing 1 over the square root. And that's a much harder question to guess on, okay? And furthermore, would you guys suppose that if your initial guess is better, what happens after you do 1 iteration of this sort of improvement process? It gets closer, right? So maybe you only have to do 1 step of the iterative process rather than 2 or 3 or something, okay? Which means less work to get a roughly accurate answer. Okay, so what we've done by doing this, take a float, pretend it's an int, shift it, subtract it from this crazy old number, and now pretend it's a float again. We did that with the number 2, okay? And what did that get us as a floating point value. 0.716 blah, blah, blah. That's pretty good, right? Because what's the true answer, so to speak? 0.707 blah, blah, blah. Dang. Right? I mean, I almost feel like I should, I can just imagine the clickbait titles for ads I could put on all the tech sites. Compute inverse square roots with this one weird trick. Yeah. Okay. Lose belly fat with this, and they always show a rotting banana for some reason, but whatever. Yes. They don't want you to know, blah. Okay. So that's pretty cool, right? That look how with some really clever work, we were able to um, get a pretty dang good estimation. Okay, now let's go back to Carmack's code, because the last step I'll leave you guys sort of on your own with, which is to compute this. Okay, that's just a Newton iteration, right? In this case, but all it is you've got a floating point number, you've got some floating point numbers that you're going to multiply, you're going to subtract, and then you're going to multiply by this other floating point number, right? This is just a bunch of multiplications and subtractions. Can you guys handle that? I would hope so, okay? And what's interesting here is notice that Carmack in the source code actually had a second copy of the iteration, but he commented it out, okay? And the comment is second iteration, this can be removed. Okay, so in testing, he must have figured out that it wasn't necessary to have that in there. The second iteration would improve the accuracy, but it wasn't needed, like the accuracy improvement wasn't needed for his purposes. Okay, because, well, let me talk about that. Why did Carmack need to compute 1 over square roots of numbers? Well, Quake, but yes, this is from Quake 3, which was first released in 1999. Okay, so in computer graphics and physics, often you need to compute, you have a vector, and you need to compute a vector of unit length that points in the same direction. Well, the length of a vector you get by doing a square root, right? Square root of the sum of the squares, Pythagoras' theorem. And if you want to make something unit length, you divide by that number. Well, if that number is a square root thing, then you're dividing by a square root. That's why I needed to do it for in computer graphics, right? And Quake 3, right? How many of you guys have ever played Quake 3? Yeah? Know what it looks like? Well, maybe you have some homework, okay? It basically it was for the 3D graphics routines, right? To compute lighting and other things in the graphics. And I guess for his purposes, one iteration was good enough. Okay, so here's a really interesting research question. Let's suppose that you took the Quake 3 source code, or the original, the Quake 3 game, and you compiled it, and you ran the game with this code as is. Okay, you'd play Quake 3 just the way he released it. What would happen if we removed the comment and did a second iteration? Well, it wouldn't be 4K graphics, but it would change things, right? Because the computations, it might slow things down a little bit. But if we put those two screens side by side, could we even notice a difference? We'd probably notice a slowdown. Maybe it wouldn't be by much, but there would be a slowdown. Okay. Would we be able to notice the graphical difference? And for that matter, what about if we comment out both iterations and we only use this kind of pretty good but not perfect estimation. Would we be able to notice that? Probably. I don't know if he ever tested that, right? But it's sort of funny. So a year and a half ago, I gave a talk on this exact algorithm back in Texas, not with the assembly, just kind of concentrating on the C. And I said, one of the questions I have is what would happen on period hardware, okay, meaning at that time a Pentium 2 was a pretty uh, the hardware maybe that if you were a bleeding edge gamer you had a Pentium 2, okay? Um, what would that look like on period hardware? And literally the next day, IT sends me an email to say, hey, so and so dropped off this old like 90s computer. Do you want it? Because they know I collect vintage stuff. And guess what processor was in it? A Pentium 2. And I'm like, perfect, I can test this. Okay, I haven't gotten around to it yet, but interesting research question, I think. Okay, good for now. All right, so next thing. Um, let me. All right, I'm not usually a PowerPoint guy, but I'm going to switch over to a PowerPoint for just a minute. So we can start briefly talking about where we'll pick up after break, which is what's called SIMD. Okay, the floating point units in ARM v8 and now also v9, okay, actually are far fancier than I've let on. In fact, there are 32 vector registers called V0 through V31, and they can be subdivided in interesting ways, okay? And they can be subdivided as 2 double precision, 4 single precision, 8 half precision, or 16 bytes. I'll show you a diagram of this in a second. Here's what it looks like, okay? So all of these registers are physically the same thing, okay? I can have a double precision that's 64 bits wide, single precision that's 32 bits wide, half precision that's 16 bits wide, or bytes, which are 8-bit wide, right? And I can treat one individually. We've basically always done the top half of this, where we've only thought of a single floating point number at a time, okay? But, and I can also actually think of a 128-bit number at a single time in a vector VN register. But what's neat about the V register is I can subdivide it in lots of interesting ways, okay? And so what I can do is, let's say I have an array of 4 single precision floating point numbers. I can store all 4 of them in one register by using let's say V0 dot 4S, and then saying, okay, the first one is this, the second one's that, the third one's this, and the fourth one's that. And they're all 4 kind of packed into a single register, okay? And then I could do that with lots of the other vector registers. Okay, now why might this be useful? Let me take an example here. Okay, a computation you have to do lots of in either linear algebra or physics or computer graphics. How many of you guys have ever heard of the dot product? Yeah? Okay, so the dot product of 2 numbers or 2 vectors. Let's say I have a vector, okay? You can think of it as just being an array for now. I have an array 1, 2, 3, 4, and I have another array 4, 3, 2, 1. Okay? The dot product is defined as multiplying the corresponding elements and then adding the results. So I do first entry times first entry plus second times second, third times third, fourth times fourth, and I get a number. Okay, and that number turns out to be important in a lot of physics and other computations. Okay, so in this particular example, I get the number 30. with my 1, 2, 3, 4 example. Okay, but now how I'm going to implement this, and we'll pick up again with this um, after break, is I want to basically pack 1, 2, 3, 4 in one of these vector registers. 1, 2, 3, 4. Okay, and then the other one will be, just for the sake of demonstration, in the same numbers but in reverse order. Okay, and then here's the thing that I want to do, and this is what makes this really clever. Okay, if I do this by hand, oops, this dot product, how many operations does it take? I can do first entry times first entry, and that's an answer. Okay, so there's one multiplication. Second times second is 2. Third times third is 3. Fourth times fourth is 4. And then I have 3 additions to do at the end. Yes? What about if I could do all 4 of those multiplications simultaneously? That would be good, right? I'd still have the additions to do at the end, but that's not all that horrible. Okay, and the floating point unit on this thing allows you to do those 4 multiplications simultaneously. Okay, and this is what, okay, so SIMD, okay, is the SIMD unit of this thing. SIMD stands for single instruction, multiple data, meaning I'm going to tell it, I want you to multiply this set of things by those set of things. One instruction, but it's doing it on, in this example, 4 pieces of data simultaneously, right? Which, as you guys could imagine, that speeds things up, right? So the SIMD units, or being able to do things in sort of vector form, is certainly useful in a lot of advanced mathematics. It's certainly useful in computer graphics, but also in things like, you've got a nice movie that you'd like to watch there. Okay, how is that movie transmitted to you? It's compressed, right? Right, and you got to decompress it and render it to the screen so you can watch it. That's a lot of computation, a lot of computation. Okay, and so SIMD units, vector units, allow you to do a lot of those computations much more quickly than you would be if you had to do each of those multiplications in order rather than doing them all at the same time. And that means your movies play faster and everything's good, right, which is fun. Okay, so we'll pick up with that example right after break. Um, and I think you guys should have everything you need to do um, the floating point paper assignment, and once I post the exact details, the floating point regular assignment, and then SIMD isn't that hard. We'll talk about it when we get back. Good? All right, some of you owe me a lot of code, so I hope you're very productive next week. And have a great break.